Okay. Let's see if I want to say something before that. I'll go back to this these strange Carnot cycles for a second. Okay. So it seems that if I can work above the freezing point of water heater and below the freezing point of water heater, I can get a perpetual motion machine that I keep on absorbing heat at both sides. Okay? This is not true. This is a problem in Sommerfeld's book on statistical physics, Sommerfeld, and he answers his response is that there are no adiabats which connect states of LV greater than 0 or LV less than 0. You don't find any adiabatic curves which will connect these two states. And these are called strange Carnot cycles. So I can work below or above the cycles. So Carnot also describes this as these cycles as being the most efficient ones possible. Why is this? Because if I can get another cycle which is more efficient than Carnot's cycle, I can always use that cycle to run Carnot's cycle in reverse, because I have more energy. So I can produce a perpetual motion machine. This he learned from his father, Lazare Carnot, that he refuted as having any other cycle greater than his. Okay? Now, when Clausius came onto the scene, what did he do? He introduced a functional state U is equal to Q minus W. That is, over a cycle, U would be a state function. So I would go back to the initial state, and I would just have the work equal to the heat. But at any point along the cycle, the difference would be attributed to an internal energy. This would be his idea of mechanics, because if Q is equal to 0, I get back mechanics. And he introduced entropy into it as Q divided by T. Okay? Because the fact is that Q1 over T1 is equal to Q2 over T2. Okay? And the fact is, if I can add up any amount of these over the system, take this Q with respect, it takes the sign, I can just say the sum of these is equal to 0. So that going around a cycle, this sum would be always equal to 0. Okay? And so this is the second law. So S, the integral of S of the cycle is equal to 0. The sum of the entropies of all the systems is equal to 0. So the question is that since entropy meant change, he assumed that the irreversibility built in was the fact is that if I decide to give off the heat at T2 at a higher temperature than necessary, then the change in entropy would be less than, would be greater than 0. Okay? I said less than because that was what Tate used. Tate got the thing confused and had ds less than 0. So over a cycle, then, if irreversible processes were involved, that the entropy would be increased. So that's the first law. The internal energy, or the energy of the universe, is constant, and the entropy increases. The question is, how do you define entropy if you don't define it like this, according to its definition as the ratio of the heat absorbed at the temperature at which it's absorbed, and the heat which is given back which is negative here, at the temperature which is given back. So he relegates all irreversibility to the second law, and irreversibility, that is, U is a function, always a function of state. Carnot, on the other hand, knew the second law, but didn't know the first law. So that he could have said that the work is equal to Q1 minus Q2 minus delta E. Okay? Where delta E is the change in internal energy from one state to another. So in this case, he would have delta E always greater than or equal to 0. That would be his condition of accessibility. And he would keep the second law as S, the sum of S, equals to the sum of Qi over Ti. So this would be Carnot's idea of what thermodynamics should look like. That is, in any case in which I have irreversible processes going on, the work would be less than that given by heat, the difference in the heat. And S is always a constant. Whereas Clausius would say E, not U, is equal to Q minus W, but that S, ds, can be greater than 0. So these are equivalent ways of looking at things. The thing is that we want to look now at the efficiency of a cycle.
Sorry,
yeah.
What is the difference between E and U?
It's U. It's the same.
Okay.
I'll keep it at E. Okay? So this is Carnot's interpretation. This is Clausius. So we want to go back and look at exactly what is the efficiency of this and whether or not that we can maximize efficiencies. So I can look at the heat over a cycle is equal to V d Vc Tc T2 T1, sorry, LV over T in dV in dt. Now, instead of taking the integral from VA to VB, I can take it from VD to VC, and according to Maxwell, you fix the state D such that the ratio of VA to VD is equal to VB over VC. VC over VB. Okay? This is the only parameter involved. VD to VA. This is the only parameter involved in everything. So that the ratio of the volumes in the two cases must be equal. So I can therefore take it from VD to VC, and if I do this, and I split the integral, this is T2, T1, dt over T. Now, the thing is that I can introduce here an efficiency. I can take the reservoir at the second temperature, at the cold temperature, and I can look at this as a type of maximization process in which this is T1 over T2. Is instead of taking the efficiency as the difference in temperature, take it as the ratio, logarithm of the ratio, and I can use the fact that log x is always less than or equal to n, x 1 over n. This is inequality for n greater than 0. And if I do that, I come out with the fact that, and I introduce Q2 is equal to Q1 over T1 times T2. Put that in there. And I get Q1 T2 over T1 log T1 over T2. And I can introduce this inequality here, which is less than or equal to Q1 T2 over T1 T1 times T2 minus 1, which is equal to Q1 1 minus T1 T2 over T1. So in this case, this is the Carnot efficiency, which I've gotten from a less effective efficiency, T1 over T2, using the cold reservoir as the heat source.
Why that in that equation?
Why this?
The Q1 doesn't play a role.
How do I know that it's according to Carnot, it's conserved? Okay? If it's conserved, I can use either one. But the fact is that if I put Q1 here, the game is over because I know that Q1 has the Carnot efficiency. So what I want to do is to construct a function which has a less efficient, which has as an upper bound the Carnot efficiency. Because Carnot efficiencies don't exist in the world. There's not a machine which works at the Carnot efficiency. Carnot wasn't upset about this. He says, I want to find the principles. I'm not interested in the practical nuts and bolts of it. So in this case now, the interesting thing is that if you look at this efficiency here, okay, that is minus x log x. Okay? That maybe not looks like anything, but it's, if you put in probabilities for this, this becomes the Gibbs entropy of the system. Okay? This is a concave function, and concave functions are supposed to be maximized. Okay? Just in reference, a black hole entropy is convex. You minimize those, and that has no property of entropy at all. So you look at concave functions which are to be maximized. And by using this inequality, what we have done is to maximize this. Okay? This inequality here to the Carnot efficiency. So I looked at these types of efficiencies and found that they were much closer to real efficiencies than the Carnot efficiency. Okay? So I can do something else. I can take a look at this and approximate the logarithm as a mean, arithmetic mean, of the upper and lower bounds. This would be T1 less than log T1 over T2 less than or equal to T1 minus T2 over T2. Okay? So I want to use these bounds to approximate this, and I can say that the logarithm of T1 over T2 is approximately equal to T1 minus T2 times 1 over T1 plus T2, which is equal to T1 squared minus T2 squared over 2 T1 T2. I can approximate it like that. And if I do, I can show you that the efficiency is equal to 1/2 1 minus T1 T2 squared. So when I start to approximate this, these efficiencies are less than the Carnot efficiency. I can also do something else and show you that the work is less than the Carnot's work. And you can see that by writing the work is equal to Q2 T2 over T1 log T1 over T2. I can introduce now the Q's because this is equal to Q2 Q1 over Q2 log Q2 over Q1 2 1. Okay? This cancels with this. What?
Maybe it's the opposite in the
No.
logarithm. Because
This?
yes.
No, because T1, Q1 over T1 is equal to Q2 over T2.
So you
I'm using Q1 as the condition for reversibility, the existence of entropy. And I can suppose that I can do this with many systems. So I put an index here, and I put the sum. Okay? More than one. And now I introduce an inequality, which is called Jensen's inequality, which says that the sum of the Qi, 1i, log Q1i over Q2i is less than or equal to the sum of Q1i log sum of Q1i sum of Q2i. Okay? This is called Jensen's inequality. And if we use the approximation for the logarithm, that is log x is less than or equal to 1 over x, this will be less than or equal to the sum of Q1i, this is the cold, sorry, this is 2. Because, hold on, this is Q2 over Q1, and this is Q2. This is Q2, so this should be Q1. And if we come out with this, we come out with Q over Q2i, Q1i, this is Q2i, and this minus 1 equals the sum of Q1i minus Q2i, which is the maximum work. So these two inequalities for concave functions, will show you that this work is always less than the work that I would get, even if I use the hot reservoir temperature, the heat absorbed at the hot reservoir. So in this case, Carnot would say that the internal energy will exist only when maximum work is performed. Okay? So he's putting the irreversibility into the internal energy and not into the entropy. And so I can write W is equal to minus Q1 x log x, as I did here, the minus sign here to invert them, And this is equal to 1 minus x Q1. This would be the Carnot's efficiency. This is the efficiency which is inferior, but I have to subtract. And this, because this will be always greater than that. Okay? So now I can bring this to the other side. Delta E is equal to 1 minus x plus x log x Q1. Okay? I just collect these terms. And this, now, I can introduce that this is less than or equal to 1 minus x plus x squared minus x, because log x is less than x minus 1. Okay? Here. And this is Q1. This is equal to 1 minus x all squared Q1, because it's a perfect square. And this is equal to the Carnot efficiency times the work, maximum work. So in this case, the upper bound, the change in internal energy, is given by this. And not only that, but you can see that delta E is equal to 1 minus x plus x log x Q1. And again, I can introduce this into here, and that delta E must be greater than 0. Okay? Because I have the x minus 1. Okay? So in every case, delta E must be 0. I must increase the internal energy as a condition for accessibility from any state A to any state B. This is Carnot talking again. Okay, the last part, very briefly, would be to introduce, to show you that the laws of thermodynamics can be written using the Carnot's equation, or principle, is halfway between the first and second laws. Okay? Just just to repeat this principle again, W is equal to P dV over a cycle, which is equal to the area under the curve, dP dV, is equal to some function, T1, T2, times Q1 or Q2. He didn't discriminate between this. I put in a symbol here, a wedge symbol. It's like a cross product. And it's easy to show that the laws can be written in a very fashion. I take a vector r, and it has dr, which has components dv and dt. dv and t are independent variables. dp and dt, if p and t are independent variables, and dv p. Okay? We know that in thermodynamics there is no line element that can be written. There is, but we can look upon as these vectors pointing out from the planes of vt, pt, and v and p, vp. Now we can create a force. The force is the negative pressure here, analogous to it because it's the area divided, the force divided by the area. 0, V 0, and Vp. Then we can look at a heat vector H, which is LV, CV, LP, CP, and P and T. And then we can introduce a gradient operator, which has two components, dI and dJ. Okay? And we can write the first law, and I'll show you how it works. Nabla wedge H minus nabla F is equal to 0. That is the cross product, the curl of H, and is equal to the curl of F for the first law. And how would that look like? Well, I can introduce dV and dt as derivatives, and I can look at the cross product of LV, CV, and that must be equal to dV in dt minus P0. So this operates as this times this, which would be dCV in dV, minus this times this, which is dL in dt, equals, in this case, plus dP in dt. Okay? This law is the exactness condition for the internal energy. That is, if I write dE is equal to dQ minus P dV, this is equal to LV minus P. Okay? In the case of an ideal gas, LV, the latent heat is equal to P, and the internal energy is only a function of temperature. In general, though, it would not be true. LV is greater than P, but the condition of the exactness condition of E on this would be dLV minus P over dt equals dCV dV. The second mixed derivatives are equal, and this is what this says. Okay? This is the first law. The second law introduces a so-called integrating factor, T, and this would say that the curl of the heat vector plus 1 over theta H is equal to 0. Okay? Theta being the integrating factor. If theta is equal to minus T, this would be equal to dV dt LV CV plus 1 over T dV dt T to the minus 1 L. And this is just minus dP in dt plus LV over T is equal to 0. Okay? This, again, is just the Carnot Clapeyron equation. And finally, I can take the difference of these two and obtain again, in this case, Carnot's equation again. So subtracting the two of them, which is again give me Carnot in this case. So the integrating factor here, theta, is just C, T itself, C function, Carnot's function, and you can see that by taking dq equals LV in dV plus CV in dt, multiplying it by c to the minus 1, c to the minus 1. And in this case, if you do that, the conditions for being exact is dLV in dt minus 1 over c dc in dt LV equals dcV in dV. And this becomes, then if you know that dP in dt equals dLV in dV, which we obtain from this d, this is t, we come out with dP in dt equals d log c in dt times LV. Okay? Again, the Carnot-Clapeyron equation. So, Carnot's theorem is that the ratio dP over dq, the area, is equal to dP in dt, dP in dV, dq is the heat absorbed, which is LV in dV. I can introduce this into here now, which is LV over T1, the hot temperature. dt, WV's cancel. So this would be equal to T2, T1, LV, T2 over T1 minus T2 over T1. The LV cancels too because LV is in the denominator, and this just becomes the Carnot efficiency. And Carnot said that the efficiency depends only on the temperatures of the two reservoirs and independent of the substance, the working substance. Okay? So, in conclusion, I would say that people have been looking at Carnot cycles and playing with them, and about 35 years ago, 36 years ago, they came out with something called an endo-reversible engine.